Hello. Today we're going to look at our second method for finding volumes. We've already seen the disk method, disks and washers last time, and today we're going to look at finding volumes by cylindrical shells, or as it's known, the shell method. Okay, so how does the shell method work? Okay, so first we're going to think about this kind of shape here. So you can think of this as maybe like a Coke can. Okay, so think about a Coke can. We'll take the top and the bottom off, so we just have kind of the round piece, the cylindrical piece that your hand holds. I'm going to think about the area, so the outside area of that cylinder. Okay, so as you can see on the diagram, take the cylinder and let's make a cut, okay, along the dotted line there. And if you think about it, if you open that out, it's gone from being kind of a complicated cylinder, it's actually just a rectangle, right? If you flatten that piece out, the height of the rectangle, the h is obviously just the height of the cylinder. The width of the rectangle, well, let's think about this. If the radius of the shell, the cylinder here, is r, the width of the rectangle is actually just going to be the circumference of that circle. Okay, it'll go around there. And so the circumference of the circle is, of course, just 2 pi r. Therefore, we have height h, we have width 2 pi r, so of course the area of that rectangle is 2 pi r h. Okay, and we're going to need that as we build this up. And as we've seen previously, let's take the sort of the three-dimensional version of this. Okay, so obviously if we really were to take a Coke can and take the piece and sort of flatten it out, although it's very thin, it does have a little width. Okay, not a lot, but a little bit, and of course we'll call that delta x, as we've done lots of times. And if we call that delta x, we now have this piece, this cuboid, which is very flat, which has a volume. And the volume of that is going to be 2 pi r h, which was the area of our rectangle, multiplied by the delta x. Okay, that gives us a volume there. And we're going to take kind of lots of these little shells and build them up to make a solid shape. And we'll maybe take some nice diagrams to see how we do that. Okay, so just consider for a moment the function 1 over 1 plus x squared. Okay, so it looks something like this, and we're going to curtail this piece. We're just going to have it go from 0 to 1, and we're going to take that and we're going to rotate it around the y-axis. Okay, so here's the function. Now we can see, well, we've just taken this from 0 to 1, so this is just the piece of the function we want. And this is going to be the piece that we're going to rotate around. Okay, this d to c is the piece that we're going to rotate around the axis here. It may help a little to see in the 3D here. You can see we're going to take this, we're going to take it kind of around here. Okay, and it's going to go from 0 to 1, so as we slide it along, you can see it's going to be the highest point there at 0 when x is 0. I'm going to drop down when x is 1. And so now if we take a different view, okay, if we take this and we've now rotated this around the axis just as we said we were going to do, and again now as we sort of slide it along, if we take it, it goes close to the origin, it gets a bit taller, but it's a very thin the radius of that shell. As we get further away, the radius gets larger and larger, but the height gets smaller and smaller until we get kind of the widest shell here. Okay, and now if we take that shell and we put kind of a trace on it, so it will follow it along as we move it around, you can see it's sort of filling in now to create this solid as it goes forwards and backwards. Ooh, isn't that pretty? Okay, so just move it around a bit. Well, from the base, it doesn't look that interesting. It actually just looks like a cylinder. But if we look at it this way, you can see the solid forming, and maybe from over here, yeah, maybe that's a better view. You can kind of see how the solid forms. That's a nice shape. Okay, so we formed our solid of revolution, and now we're going to find the volume of that. Okay, so here is our key idea, our formula that we'll be using. Okay, so we're taking some region R, it goes from x equals a to x equals b, and we're revolving that region around a vertical axis, perhaps a y-axis or perhaps a different vertical axis. Okay, well Rx is the distance of the axis of rotation to the value x, in other words the radius that we've been looking for, and h of x is just the height of the solid at some value x. Then our volume is given by this. Now recall we had that sort of 2 pi r h delta x. Well, here we're simply taking the limit of the sum, and of course that's created an integral for us. We've taken the 2 pi outside that integral. and we have the Rx multiplied by Hx, which are varying as x varies. Okay, so our volume is given by 2 pi, then we integrate from a to b Rx multiplied by Hx. A couple of notes on that. If the region is bounded above by f of x and below by g of x, then that high h of x is f of x minus g of x. And if the axis of rotation is the y-axis, then the r of x is simply x. Okay, we're rotating around the y-axis, then the distance away, the radius we're going to get is simply x. Now we can have a different vertical axis, and we'll see how that changes as we go along. Okay, take a couple of examples. Okay, here's our first example. We're going to find the volume of the solid formed by rotating the region bounded by y equals root x, y equals 0, and x equals 1 about the y-axis. Okay, so always in these cases I recommend drawing a picture. You don't need a 3D picture, a 2D picture is just fine. So let's take, something like this. Okay, so here we have the function y equals root x. We're bounded by y equals 0 and x equals 1. So I've just curtailed the function, it stops at 1 there. And you'll see I have that vertical line somewhere in there. Okay, that's just some sort of typical line, and that's something we would rotate around the axis. Also, you'll see I've bolded the y-axis, that's what we're rotating around. Okay, so we're going to take this piece and rotate it around this axis, and that's really everything we need. Okay, the diagram helps us see, hopefully we can see that the height is going to be root x. The Rx, the radius, is simply going to be x because we're rotating about the axis, and we're going to integrate from 0 to 1. And so sure enough, our volume is simply given by 2 pi, it's always there. Integral from 0 to 1, and we have root x multiplied by x. And of course, that's pretty straightforward to integrate. That's just x to the 3 halves, which of course we can integrate, and we get 4 pi over 5. Okay, so that's pretty straightforward. Let's take a slightly more complicated one. Okay, so now we're talking about the region bounded by y equals x squared minus 2x plus 2 and y equals 2x minus 1. We're going to take that region and rotate that around x equals negative 1, so not the y-axis anymore, to form a solid. Okay, so again, first stage, maybe we'll just draw a picture. So those are the two functions we're talking about. The blue line is the x squared minus 2x plus 2. The other line is the 2x minus 1. Okay, and it mentions that it's the region bounded by that, so obviously it's sort of inside here. Okay, so maybe I'll draw a second picture. Okay, so I've just taken that region, just the region we're interested in. Again, I have my sort of typical little slice here, my typical piece that's going to form a shell. And obviously I have my axis that I'm rotating it around now, okay, which is no longer the y-axis. Okay, so the height is clearly just the high function minus the lower function, that's the h of x. The radius, well, if this distance is x and this distance is 1, then this distance must be x plus 1. Okay, the functions vary from 1 to 3. The 1 and 3 are actually where the two functions meet. And so our integral becomes this. We have 2 pi, we integrate from 1 to 3. We have 2x minus 1, the higher function, minus the x squared minus 2x plus 2, the lower function. And we mentioned before our radius is given by x plus 1. And we say this so often when we're doing these applications, this is a pretty straightforward integral. Okay, we have a bit of algebra to do, and we have to multiply by that x plus 1. But there's nothing particularly hard about this integral, it's the setup that's difficult. So I'll skip all the steps, and the integral there in fact becomes 8 pi. Okay, so that would be the volume formed there. Okay, and that's about it for cylindrical shells.